In this video, we are going to be discussing on the reactions of alkylbenzene. Reactions of alkylbenzene. But before we continue, I want to thank those of you who have taken your time to subscribe to my channel. For those of you who haven't subscribed, please take your time, subscribe to the channel, like our videos, and then share to fellow learners who will be writing exam next year or in 2 or 3 years. Thank you for taking your time to subscribe to our channel. Let's get started. Reactions of alkylbenzene. Reactions of alkylbenzene. You know that benzene, all alkylbenzenes these are compounds having alkyl groups on the benzene ring. But how is benzene produced? Benzene can be produced from ethane. It can be produced from ethane by heating ethane with red hot copper. If ethane is heated with red hot copper, you can equally get a benzene, or with iron tube, you can equally get a benzene. So benzene, as I said, can be produced from ethane. In this, let me give you the equation. This is ethane. You can have benzene. Here you could use, as I said, iron tube, red hot copper, red hot copper, red hot copper, heated red hot copper. This is ethane. This is ethane, and this is benzene. So if you do that, you can get benzene. Now, our subject today was, or is, reaction of alkylbenzene. We will be starting with halogenation of methylbenzene. We'll be starting with halogenation of methylbenzene. Let's say halogenation of methylbenzene. The reagent for the reaction is any halogen, let me say chlorine, or bromine gas. The condition is a halogen carrier. It could be aluminum chloride or iron 3 chloride that will be acting as a catalyst. If we are using chlorine as the reagent, the product would be 2-chloro and 4-chloromethyl benzene. Would be 2-chloro or 4-methyl benzene. Generally, we can call it haloalkylbenzene. The condition, once more, is a halogen carrier. It could be aluminum chloride or iron 3 chloride that will be acting as a catalyst, not UV light. All these, not UV light. It should be noted that for this reaction, it should be noted that this is how the reaction will go. Methyl benzene, we will have this methyl benzene. This is methyl benzene. And the methyl benzene, what is going to happen here is that a methyl benzene, the methyl group is electron donating. The methyl group is electron donating. It will activate the ring. It will activate the ring, and it will activate the ring at the position of 2, 4, and 6. These positions here, this is what is going to happen. The positions here, 2, 4, and 6. So this is electron donate. This is an electron donating group. Is going to activate the ring. It's going to activate the ring. There's going to be an increase in the electron density in the ring. So when it increases the electron density at the 2, 4, and 6 position. It increases the electron density at the 2, 4, and 6 position, thereby activating the ring for electrophilic attack at the 4th, at the 2nd, the 4th, and the 6th position. That is why we say the methyl group is electron donating. It activates the ring at the position of 2, 4, and 6. It increases the electron density of the delocalized the electron density of the delocalized electron system of the benzene ring. For this reason, it activates the ring so that electrophilic attack will take place at the 2nd, the 4th, and the 6th position. These positions are where electron density is high. In other words, we can say this group, the methyl group, is 2, 4, 6 directing. It is 2, 4, 6 directing once more because it increases electron density at the 2, 4, and 6 positions, thereby initiating electrophilic attack at these very positions. So that any incoming group will be directed to the 2 position, the 4th position, and the 6th position. For halogenation, this halogenation is not going to take place here. It is going to take place in the ring. It is the halogenation is going to be substitution at the second, the fourth, and the sixth position. There's going to be substitution. Going to substitute the hydrogen at the second, the fourth, and at the sixth position. So this is what is going to happen now. Showing K, now we are reacting with hydrogen. With chlorine plus chlorine. We will have at this position, you will have chlorine and steamy fumes of hydrogen chloride. So what we will have here will be, this is methyl benzene. This is 2-chloromethylbenzene. And this is hydrogen chloride. Now, I said at the second and the fourth position. Now, at the fourth position, we will also have this we will be having we'll see how this as methylbenzene. We'll have this as 4-chloromethylbenzene. So, as I was saying, I said the condition for this halogenation of this methyl benzene. Methyl benzene is an alkyl benzene. It's an alkyl benzene. The condition is we are using but a halogen carrier. We are not going to use UV light. And When it happens, we are using methylbenzene. Being the methyl group, a methyl group is an alkyl group, and an alkyl group is electron donating. It's an electron donating. It increases the electron density at the second, the fourth, and the sixth position. When it does this, when it increases electron density at these three positions, it does what? It helps to activate the ring for electrophilic attack to occur at these positions, so that any incoming group, for instance, like the chlorine is the incoming group. Chlorine is being directed for electrophilic attack at the second, the fourth, and the sixth position. So for that reason, we call this group 2,4,6 directing. We call this group 2,4,6 directing because that is where electrophilic substitution is taking place. We will move to the next group. The next one will be the next condition. We will, for the next one, that we use the same. We are going to use the same reagent, but the condition will change. In this case, we are going to use chlorine or bromine. We are going to still use chlorine or bromine, but the condition is UV light this time around. UV light. We are going to use UV light and not a halogen carrier. The UV light is going to act as our catalyst, not a halogen carrier. And in that case, the substitution is not going to take place on the ring. The substitution will be taking place, but on the alkyl group. The substitution will be taking place, but on the alkyl group. So it should be noted that where a halogen carrier is being used, the substitution of the incoming group will take place, but on the ring. But when a halogen carrier is used, substitution will take place, but on the alkyl group, that is on the benzene ring. So in this case, where we are using but a UV light as our catalyst, the substitution is going to take place in the alkyl group. So we will have here the methylbenzene. We have methylbenzene here. Methylbenzene plus chlorine. Methylbenzene plus chlorine. We would be having I said the substitution is going to take place, but substitution into the alkyl group, not on the ring. Here we will have in that case, we will be having, in that case, our product here will be chloromethylbenzene. Chloromethyl chloromethylbenzene. Chloromethylbenzene. So now, even though even though the methyl group is electron donating, even though the methyl group is electron donating, it doesn't. The condition of the reaction has changed. The reaction is not going to be taking place this time around on the benzene ring. It's going to be taking place within between the alkyl group and chlorine. So substitution is going to be in the alkyl group, not on the benzene ring. So now it is a continuous process until all the hydrogens there are all substituted as halogenation. We will have we can now substitute for use chloromethylbenzene for the reaction again. And our product here would be dichloromethylbenzene. Dichloromethylbenzene, that will be our product. Dichloromethyl Dichloromethylbenzene. The reaction continues until all the hydrogens are fully substituted. So now we'll be reacting with dichloromethylbenzene. and our product will be trichloromethylbenzene. Will be trichloromethylbenzene. That will be our product. Trichloromethylbenzene. So when we do this, that is a that is the halogenation of an alkyl benzene using a UV light. So we can proceed to nitration of alkyl benzene. Nitration of alkyl benzene. Our reagent in this case is concentrated nitric acid. We will be using concentrated nitric acid, and we will reflux. The reaction mixture will be reflux at a temperature less than 30 degrees Celsius. In the presence of sulfuric acid, that will be acting as a catalyst. So nitric acid and sulfuric acid mixed at this temperature and reflux, we will have a nitronium ion, and this nitronium ion will be substituted. The nitronium ion will be substituted again at the second and at the fourth position, since we said the methyl group is 2,4 directing. The methyl group is 2,4 directing. Just as I said, they help to increase the electron density in the ring, and in that case, they activate the ring and initiate electrophilic attack at the 2,4,6 position. So when a concentrated nitric acid is mixed with concentrated sulfuric acid and reflux at a temperature less than 30 degrees Celsius, we will have nitromethylbenzene, and it will be a 2-nitromethylbenzene and a 4-nitromethylbenzene. But should in case the temperature exceeds 30 degrees Celsius, we will have 2, 4, and 6. But in most occasions, this is rare. So now the product for this reaction here would be reacting concentrated sulfuric acid and nitric acid. We will have a nitronium ion. The nitronium ion will substitute. This substitution in the benzene will substitute at the second and the fourth position. If you want to know the details of the mechanism of this reaction, please refer to our previous video on nitration of benzene. If you want to know the mechanism of this reaction, I will advise you to watch our previous video on nitration of benzene. But in this case, it's still the same. It is still the same thing. But I will just give you the product of the reaction. So methylbenzene, methylbenzene will have say it is 2,4 directing plus methylbenzene plus nitric acid. The reagent is concentrated nitric acid. Concentrated nitric acid, we will have the NO2 will be at the second and fourth position. Will be at the second position. Plus water. And the product of this, the main product from here is 2-nitromethylbenzene. 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 Now, again, since we said the methyl group is 2,4,6 directing, the second product will also be 4-nitrobenzene. That will be 4-nitrobenzene. You will have this. This will be 4-nitrobenzene. For 4-nitrobenzene, there will be 4-nitrobenzene that will be formed there, and a molecule of water. So this is 4-nitrobenzene. 4-nitromethylbenzene, sorry. 4-nitro 4-nitromethylbenzene. So now we will proceed. We will proceed to oxidation of alkylbenzene. Oxidation of alkylbenzene. Oxidation of alkylbenzene. We'll proceed to oxidation of alkylbenzene. It should be remembered that oxidation of alkylbenzene has to with oxidation of alkylbenzene, even though the methyl group is 2,4,6 directing, but in this situation, the mixture is heated under reflux, and the reagent is acidified potassium manganate 7. When acidified potassium manganate 7 is heated, is mixed with methylbenzene and heated under reflux, there is what we call a side chain oxidation. The reagent acidified potassium manganate 7 is an oxidizing agent. It should be noted that acidified potassium manganate 7 is an oxidizing agent. And what is oxidation? Oxidation is the addition, when it has to do with organic compound, addition of oxygen into a compound with subsequent removal of hydrogen. There's addition of oxygen with subsequent removal of hydrogen. So in this situation, oxygen is being added to this compound and it is on the side chain. So the oxidation is not taking place in the ring. The oxidation is taking place on the methyl group. The oxidation is taking place on the methyl group. And the methyl group is always oxidized. The methyl group is always oxidized to a carboxylic acid group. So this acidified potassium manganate 7 is used to oxidize the side chain. In this situation, the side chain here is the methyl group. So the methyl group is oxidized to the acid group, to the carboxylic acid group. So see how the whole thing goes. Let me write the equation for you, and you see it. It's methylbenzene as our example. Methylbenzene as our example is this one. So you will see that the acidified potassium manganate, the acidified potassium manganate 7 is used to oxidize the side chain, which is the methyl group, to the corresponding benzoic acid. We oxidize it to benzoic acid. This is benzoic acid. From methyl benzene to benzoic acid. So as I said, that the reaction mixture is heated under reflux. This is under here reflux, and here oxygen will substitute the hydrogens here to produce the acid, and one of the hydrogen, the other hydrogen, two of the hydrogens are now taken with two atoms of hydrogen, two atoms of oxygen to produce, one atom of oxygen to produce a molecule of water. So we use two atoms of oxygen here, and one is left that is used with two atoms of hydrogen. then a molecule of water is being produced. So, so it should be noted that in any other in any other reaction, when given any other reaction that has to do with acidified potassium manganate, all carbon side chain groups, all alkyl groups, or any carbon side chain group is always oxidized to the carboxylic acid group under this condition. For instance, I will be using this other one. Another example of this is, let's use this, an example of 1,4-dimethyl benzene. 1,4-dimethyl benzene, you see that the side chains are oxidized to the corresponding acid groups. So you have this here. You also have this. This time around, we will need 6 atoms of oxygen, because we are going to oxidize 2 side chains. Side chains. We have this, or if that is taken into consideration, we will have manganate, acidified manganate 7, acidified manganate 7 ion. When we reflux it, our product will be a dicarboxylic acid. Our product here will be a dicarboxylic acid group that will generate. We will have this plus 2 molecules of water. We will have this plus 2 molecules of water that will be formed. Have that 2 molecules of water. Again, we could still have, this is the first example for this side chain oxidation. That is the first example. This is the second example, and this is the third example for this. The third example, we are not going to use a methyl group. We are going to use but an ethyl group in this situation. We are going to use but an ethyl group in this situation. See what the outcome will be. Here, okay. We are going to use this again. The reaction condition will be, we will have have this. Okay, plus. What we have here is this O2. Well, the same condition. Under reflux. So you will look at this. This will be. You will see that again. This is. This is ethylbenzene. Ethylbenzene will give us benzoic acid, still benzoic acid. So it's the same thing, as we said, is the same thing that we are going to use. You will see that we are not using methylbenzene. We are going to use but another alkyl group. That is the ethyl group. So we are using but ethylbenzene this time around, not methylbenzene. Ethylbenzene under the same condition or reaction condition. That is acidified potassium manganate 7 ion. We reflux it, and you see what is happening here. What is happening here is that only an acid is produced. Then the other carbon atom is converted to what? To carbon dioxide. The other carbon is now converted to carbon dioxide. Even if it was a propyl group here, only one acid group is produced, then the other ones will be converted to carbon dioxide and water. That is what happens. So a recap of our topic. From the onset, I said benzene is produced by heating ethane with red hot copper. When you do that, you can get a benzene. But for our reactions regarding alkylbenzene, we said alkylbenzene can undergo halogenation, but the type of halogenation that the alkylbenzene will undergo will depend on the reaction condition. Now, this is halogenation using a halogen carrier. Either you use aluminum chloride or iron 3 chloride as a catalyst. When you use aluminum chloride or iron 3 chloride as a catalyst, the substitution is going to be directly on the benzene ring. Now, initially I told you the methyl group is an alkyl group, and all alkyl groups are electron donating. They are electron donating. They tend to increase the negative charge or the electron density at the second, the fourth, and the sixth position of the benzene ring. When they do this, they activate the ring. And when they activate the ring, They enable electrophilic attack to take place at the second, the fourth, and at the sixth position. That is why we say alkyl groups are 2, 4, 6 directing, so that any incoming group is directed, any incoming group or any incoming electrophile is directed to the second, is directed to the second, the fourth, or the sixth position. This is where there is electrophilic substitution. Electrophilic substitution is taking place at those positions. Once more, electrophilic substitution is taking place at those positions because those are the positions that there's high electron density, and that is why reacting with chlorine, we had two products at this 2-chloromethylbenzene and 4-chloromethylbenzene. Then we went further to still using halogenation, but this time around the reaction condition changed. And I told you that halogenation, the type of halogenation that takes place will depend on the reaction condition. And the reaction condition in this situation is a UV light that is acting as a catalyst, no more a halogen carrier. And being a UV light that is acting as a catalyst, what is going to happen now is the substitution is not going to take place on the benzyl ring, but the substitution is going to be taking place but within the alkyl group. The substitution is going to take place at the alkyl group. There's going to be substitution. The halogen is going to substitute the hydrogen in the alkyl group until all the hydrogen atoms in the alkyl group are substituted. We substituted the first one and we had chloromethylbenzene. Then we used chloromethylbenzene to react with chlorine again. We had dichloromethylbenzene and steamy fumes of hydrogen chloride. We used the dichloromethylbenzene again to react with chlorine, and finally we had trichloromethylbenzene. So under this condition, that is the type of substitution that is taking place. We went further for the nitration of methylbenzene, nitration of the alkylbenzene. So nitration of alkylbenzene, as I told you, if you want to know the mechanism of nitration of benzene, you visit our previous video on the reaction mechanism. The reaction mechanism of nitration of methylbenzene. Now, this is an alkylbenzene, methylbenzene, that is reacting with the same reagent. The nitronium ion that gives the nitro group is produced by reacting the concentrated nitric acid and in the presence of sulfuric acid, which is a catalyst, at a temperature less than 30 degrees Celsius. All these are reflux under this temperature condition. And when we do that, as I told you, the methyl group is a 2,4 directing. So the first product that will be obtained from here will be 2-nitromethylbenzene, and the second a molecule of water. Then the second product that will be obtained again will be 4-nitromethylbenzene with a molecule of water. But if the temperature rises above 30 degrees Celsius, it can give 2,4,6 trinitromethylbenzene. But in rare occasion, this will happen. We went further to the oxidation of alkylbenzene, and we are still using methylbenzene as our example. Under this condition, nitration of alkylbenzene, the reagent for this that is used for the oxidation of this alkylbenzene is acidified potassium manganate 7 ion. Acidified potassium manganate 7. This is a strong oxidizing agent. Remember that for the purpose of revision, remember that acidified potassium manganate as an oxidizing agent helps to provide oxygen. Helps to provide oxygen. So all this reaction mixture, is refluxed, and what happens is that there is a benzoic acid that is being produced. It should be remembered that it is the alkyl group that is being oxidized. There is oxidation of the side chain. The oxidation takes place. The side chain is oxidized to a carboxylic acid group. For instance, the methyl group, the methyl benzene, will be oxidized to what? Will be oxidized to benzoic acid and a molecule of water. Then, if we are using, if I was using 1,4-dimethyl benzene, remember I told you that the side chain are the one to be oxidized. We are now going to have two acid groups here. We are going to have two acid groups. It's going to be, our product will be a direct acid. There are two acid groups because the two side chains are going to be oxidized to what? They are going to be oxidized to two carboxylic acid groups, and with two molecules of water that are being produced. If we change the alkyl group, if we now change the alkyl group from a methyl group to an ethyl group, now it's an ethyl benzene, and we want to, under the same reaction condition, we oxidize it. We are not going to have only one of the carbon will be oxidized to a carboxylic acid group. Only one of the carbon on the carbon chain of the side chain will be oxidized to a carboxylic acid group. The other carbon will be converted. The other carbon will be converted to a carbon dioxide. The other carbon will be converted to carbon dioxide and water. So do not be confused if given a methyl group and an ethyl group or a propyl group. Remember that only one of the carbon is oxidized to a carboxylic acid group. The rest are converted to carbon dioxide and water. Thank you for listening. Once more, for those who have not subscribed, please love our videos, share them to prospective learners, and most importantly, take your time to subscribe to our channel so that subsequent videos you will have them. Thank you. Have a nice day. Wishing you best of luck in your exams.